All right, so if you remember the rules for spin splitting, we use the n+1 rule. And then I'm going to talk now more about this complex splitting. If you look down where it says multiple non-equivalents, you'll notice that on those alkenes, all of the protons that are circled are actually non-equivalent. And so because of that, they're able to split with one another. All right. And then if you look at the other example where protons are diastereotopic, the protons that are adjacent to the chiral center shown here, those protons are what we call diastereotopic, because if you remove one of them and replace it with another atom, then you get a diastereomers. So I'm going to show you that now. All right. So if you have a chiral molecule and the protons or the hydrogens adjacent to the chiral center, we call those diastereotopic. They're different, and the reason they're different is because you can replace them with a different atom and you're going to get a different diastereomer. So let's look at the top example, and let's look at the set of protons on the left. So if I took one of those two protons and replaced it with a different atom, X is just a generic atom, right? You notice that I formed two diastereomers. And so what that means is that those two protons are in two different chemical environments. And because of that, they will split differently, right? They'll split each other. Because they are in different chemical environments and because of the stereochemistry. So when they couple, right, you'll actually see them coupling with one another and any other adjacent protons, right? So you can have some really complicated splitting patterns because of that. And if you look at the protons on the right that I have highlighted down here with the blue X, um, for those protons, they actually can split with one another as well, because if you take either one of those off and replace it with an X, you get two diastereomers. So because they are two different isomers, stereoisomers, then you'll actually see those two protons separately in an NMR. So the protons here, they both show up separately, right, as two different signals and non-equivalent, and then the protons on the right also both show up as non-equivalent with two different signals. All right, so let's look at this example, right? You see the two pink protons, they're adjacent to the chiral center here. And because they're adjacent to that chiral center, you're going to see each one of those protons show up as separate signals, right? And so if you look at on the right, you see I just have one of those protons replaced with a different atom so that you can see that they're actually diastereotopic. So both of those are two different diastereomers. All right, so we zoom in, we see that the green proton is showing up as what we call, again, a doublet of doublets, and then so is the pink proton. So how are they splitting with one another? Well, the green proton is going to split with the red proton that's here, as well as the pink proton that's adjacent to it. Even though it's on the same carbon, they're non-equivalent. And so because they're non-equivalent, they're going to split with each other. And then the pink proton is also going to split with the red proton and with the green proton that's on the same carbon with it, because those two protons are non-equivalent. So in the signal, you'll see that splitting pattern displayed as what we call a doublet of doublets. That's really the simplest complex splitting pattern that you're going to see. Right? What about enantiomers? Right? We talked about diastereomers, but now if you have a proton that's on a chiral center, and if you'll notice that particular proton, if the chiral center is up or wedged as it is here, or dashed as it is in the other example, it really doesn't change the proton. So that type of proton we call enantiotopic. And because it's on the chiral center, and you get an enantiomer based on whether that chiral center is up or back, that proton is those two enantiomers don't show up as different signals in the NMR, right? Only diastereomers and diastereotopic protons show up as separate signals. Okay, so let's look at these alkenes, and I'm going to talk about how you see non-equivalence there, right? So if you look at the alkene, notice there are two protons on the double bond here, and here. And then also there are 2 protons adjacent to the double bond here and here. And so if you look at the, again, the test for equivalence to see if any of those are equivalent to one another, that top example, right, that if I replace that proton here with the X, that compared to the second example where I replace this proton with an X, right, those are 2 different compounds. And because of that, that means that those 2 protons are going to be non-equivalent and they're going to show up as separate signals, right? If I replace the 2 protons here that are adjacent to the alkene with the X, right? If you look at that, I'm going to get the same compound, right? So those 2 would be equivalent to one another. They're not going to show up as different signals. Here, we're going to stop and I'm going to go over some NMR problems for NMR assignment 2. And so I'm going to go ahead and stop here. If you have any questions, just email me and we'll talk more, right? Any questions about anything, you can just shoot me an email and we'll talk more about it. Okay, thanks.